Welcome to this coding walkthrough. In this session, we'll tackle LeetCode problem number 1464, maximum product of two elements in an array. This problem is a great exercise in array manipulation and optimization. Whether you're preparing for coding interviews or sharpening your problem-solving skills, this is a valuable problem to explore. Let's dive in. The problem we're solving is to find the maximum possible value of the expression nums I1 asterisk nums J1 for an integer array nums. Here, I and j are indices of the array, and they must be distinct, meaning I cannot equal j. The input array is guaranteed to have at least two elements, and each element is a positive integer between 1 and 1000. For example, if the input array is 3, 4, 5, 2, then we need to determine the two distinct numbers in the array that will maximize the given expression. The result will be an integer representing this maximum value. In the first example, the input array is 3, 4, 5, 2. To solve this, we identify the two largest numbers in the array, which are 5 and 4. Subtracting 1 from each, we get 4 and 3. Their product is 4 asterisk 3 equals 12. This is the highest value we can achieve with this array since no other pair of numbers produces a greater product. For the second example, the input array is 1, 5, 4, 5. Here, the two largest numbers are both 5. Subtracting 1 from each gives us 4 and 4, and their product is 4 asterisk 4 equals 16. In the third example, the input array is 3, 7. With only two elements in the array, these are the numbers we must use. The values are 7 and 3. Subtracting 1 from each gives 6 and 2, and their product is 6 asterisk 2 equals 12. Since these are the only two numbers available, this is the maximum product possible for this array. Now let's consider some important constraints and edge cases. The array will always contain at least two elements, with a size between 2 and 500. Each number in the array will be a positive integer between 1 and 1000. For edge cases, the solution must handle small arrays like 1, 2, where there are exactly two elements, as well as arrays with very large values, such as 1999. Arrays with duplicate largest elements, like 5, 5, 1, 1, and arrays where all elements are equal, such as 10, 10, 10, must also be handled correctly to ensure the maximum product is calculated accurately in all scenarios. When solving LeetCode problem number 1464, the goal is to find the maximum product of two elements in an array, specifically nums I1 asterisk nums J1, where I and j are distinct indices. To approach this, we can consider a few different methods. First, there's the brute force approach. The intuition here is simple. We compute the product for all possible pairs of indices in the array using two nested loops. For each pair, I, j, where I is not equal to j, we calculate the product and keep track of the maximum value encountered. While this method is straightforward to implement, it has a time complexity of n squared due to the nested iteration, making it inefficient for large input sizes. The space complexity is 1, because no additional data structures are used. However, one major downside is that this approach becomes computationally expensive for larger arrays, especially when the size of the array gets close to the upper limit of 10,000. Another option is the sorting-based approach, which is a step up in efficiency. Here, we rely on the observation that the two largest numbers in the array will yield the maximum product when reduced by 1. By sorting the array, we can directly access these two largest values. To implement the sorting approach, we first sort the array in ascending order. Once sorted, the two largest numbers will be located at the last two indices of the array. Using these values, we can compute the result as nums-1, 1, asterisk, nums-2, 1. This method improves the time complexity to n log n due to the sorting step. The space complexity depends on the specific sorting algorithm used. For in-place sorting, it can be 1, while some implementations may require up to n additional space. The trade-off here is that, while this approach is much faster than brute force for larger arrays, sorting the entire array is unnecessary since we are only interested in the two largest elements. This brings us to the optimized linear scan approach, which eliminates the need for sorting. Instead of sorting, we can find the two largest numbers in the array with a single linear pass. To do this, we initialize two variables, max1 and max2, to keep track of the largest and second largest numbers encountered during the iteration. As we traverse the array, we update these variables whenever we find a value larger than the current max1 or max2. At the end of the loop, we compute the maximum product using these two values as max1 1 asterisk max2 1. Among the approaches discussed, the optimized linear scan is the most efficient and was chosen as the best solution for this problem. The reasoning behind this choice rests on a few key observations. First, the maximum product always comes from the two largest numbers in the array, and while sorting can identify these values, it introduces unnecessary overhead. The linear scan achieves the same result without sorting, making it more efficient. In terms of efficiency, this solution has a time complexity of O(n), because it only requires a single pass through the array, and it uses O(1) space since no additional data structures are needed. This makes it significantly faster than brute force and avoids the overhead of sorting, especially for large inputs. Furthermore, the implementation is simple and straightforward, requiring only a few variables and a single loop. Here's the Python code for this solution. The function initializes max1 and max2 to 0. As we iterate through the array, if the current number is greater than max1, we update max1 to this number and shift the old max1 value to max2. If the current number is not greater than max1 but is greater than max2, we update max2. After completing the loop, we return the product of max1 1 asterisk max2 1 as the result. This code is highly efficient, as it computes the desired result in a single pass through the array. Its low time complexity of O(n) and constant space usage make it ideal for handling large input sizes, including arrays with up to 10,000 elements. By avoiding the inefficiencies of brute force and the overhead of sorting, this approach delivers an optimal solution to the problem. It not only meets the constraints of the problem but also ensures scalability and simplicity. This makes it an excellent choice for solving the maximum product of two elements in an array problem efficiently and effectively. In this problem, we are tasked with finding the maximum product of two elements in an array, where the product is defined as nums I1 asterisk nums j1 for any two distinct indices I and j. The input array nums will always have at least two integers. Instead of trying all possible pairs, which would involve a time complexity of O(n) squared, we can use an optimized approach that only requires identifying the two largest numbers in the array. This drastically reduces the computational cost to O(n). To achieve this, we initialize two variables, max1, which will store the largest number, and max2, which will store the second largest number. These values are updated as we iterate through the array, ensuring that we only need one pass to determine the two largest numbers. Once we have them, computing the result becomes straightforward by using the formula max1 1 asterisk max2 1. Now, let's break down the steps further. During the iteration, for each number in the array, we compare it with the current value of max1. If the number is larger than max1, we update max2 to the current value of max1, essentially shifting the largest number down to the second largest, and then set max1 to the new number. If the number isn't larger than max1 but is larger than max2, we simply update max2 to this number. By the end of the loop, max1 and max2 will hold the two largest numbers in the array. Using these, we compute the result as max1 1 asterisk max2 1 and return it. This approach ensures we only traverse the array once, making it highly efficient. The key insight here is that the maximum product will always involve the two largest numbers in the array because both subtraction and multiplication are monotonic operations. This eliminates the need for exhaustive comparisons, optimizing the algorithm significantly. For data structures, we only use two variables, max1 and max2, which are sufficient to track the two largest numbers in the array. This makes the solution not just time efficient but also space efficient, as it has a constant space complexity of O(1). Let's consider some edge cases. First, if the array contains exactly two elements, the algorithm still works seamlessly since it directly handles two numbers. Second, if all elements in the array are equal, for example, nums equals 3, 3, 3, the algorithm will correctly identify the largest two numbers as the same value, and the product will compute as expected. Third, if the array contains negative numbers and the problem constraints allow them, we ensure that the variables max1 and max2 are initialized appropriately, such as using INF for negative scenarios. Finally, for large arrays, the algorithm remains efficient due to its linear time complexity, making it well-suited for handling substantial input sizes. The algorithm's time complexity is O(n), because we only traverse the array once to find the two largest numbers. This is a significant improvement over O(n squared) solutions that involve nested loops, or O(n log n) solutions that involve sorting. As for space complexity, the algorithm is O(1), since we only use two variables, max1 and max2, to store the largest numbers, regardless of the input size. Here's the Python implementation of the algorithm. We start by initializing max1 and max2 to 0. As we iterate through the array, we update these variables based on the rules we discussed earlier. If the current number is greater than max1, we shift max1 to max2 and set max1 to the current number. Otherwise, if the number is greater than max2, we update max2. Finally, the result is computed as max1 1 asterisk max2 1 and returned. This implementation is concise, efficient, and handles all edge cases effectively. Let's walk through an example to see the algorithm in action. Suppose the input array is nums equals 3, 4, 5, 2. We initialize max1 and max2 to 0. As we start iterating, the first number is 3. Since it's greater than max1, we update max1 to 3. The next number is 4, which is greater than max1, so we shift max1 to max2 and set max1 to 4. The third number is 5, which is greater than max1, so we update max2 to 4 and set max1 to 5. The last number is 2, which is smaller than both max1 and max2, so no updates are made. After the loop, max1 is 5 and max2 is 4. Using the formula max1 1 asterisk max2 1, we compute 5 minus 1 close parenthesis times open parenthesis 4 minus 1 close parenthesis is equal to 4 asterisk 3 equals 12. Thus, the output is 12, demonstrating the efficiency and accuracy of this approach. The provided Python implementation solves LeetCode problem 1464, maximum product of two elements in an array, efficiently by finding the two largest numbers in the array. The goal is to return the maximum product of nums I1 asterisk nums J1 for any two distinct indices I and j. ### explanation of the code. 1. Initialization. The variables first underscore largest and second underscore largest are initialized to negative infinity, float, INF, to ensure that any number in the array will be larger during comparison. 2. Finding the two largest numbers. The loop iterates through each number in the input array nums. If the current number is greater than first underscore largest, the previous first underscore largest is demoted to second underscore largest, and number becomes the new first underscore largest. Otherwise, if number is larger than second underscore largest but not greater than first underscore largest, it updates second underscore largest. 3. Calculation of the maximum product. Once the two largest numbers are identified, the product of first underscore largest 1 and second underscore largest 1 is computed and returned as the result. ### efficiency. The algorithm runs in O(n) time complexity, where n is the length of the input array. This is because the array is traversed only once to determine the two largest numbers. Space complexity is O(1), as no additional data structures are used, and only a constant amount of extra space is required. ### edge cases. The problem guarantees that the input array contains at least two integers, so there is no need to handle cases with fewer than two elements. All elements in the array are positive integers, so subtracting one from them will not lead to negative results. This implementation is concise, efficient, and robust for all valid inputs to the problem. This is the Java implementation of the LeetCode problem number 1464, maximum product of two elements in an array. The logic mirrors the provided Python solution, where we iterate through the array to find the two largest integers. The product of these values, reduced by 1, is then computed and returned. Key differences include Java's type declarations and the use of integer.min_value for initialization. To solve this problem, we start by initializing two variables, first underscore largest and second underscore largest, both set to negative infinity. These variables will help us keep track of the two largest numbers in the array as we iterate through it. Looking at the first number in the array, which is 3, we see that it is greater than first_largest. This means we need to update both variables. Second_largest takes the value of first_largest, which is still negative infinity, and first_largest is updated to 3. Now, moving to the next number, 4, we compare it with first_largest, which is currently 3. Since 4 is greater than 3, we update second_largest to 3 and first_largest to 4. At this point, our tracking variables are first_largest equals 4 and second_largest equals 3. Next, we encounter the number 5. Comparing it with first_largest, which is 4, we see that 5 is greater. So, we update second_largest to 4 and first_largest to 5. Now, the variables are first_largest equals 5 and second_largest equals 4. Finally, we examine the number 2. Since it is smaller than both first_largest and second_largest, no updates are made. The variables remain first_largest equals 5 and second_largest equals 4. With the iteration complete, we calculate the result by substituting these values into the formula. First_largest 1 asterisk, second_largest 1. This works out to 5 1 asterisk 4 to 1, which equals 4 times 3, giving the final output of 12. In this example, the array is 1, 5, 4, 5. We begin by initializing first_largest and second_largest to negative infinity. The first number, 1, is greater than first_largest, so we update second_largest to the value of first_largest, which is still negative infinity, and then update first_largest to 1. Now, the values are first_largest equals 1 and second_largest equals INF. Moving to the next number, 5, we see that it is greater than first_largest, which is currently 1. So, we update second_largest to 1 and first_largest to 5. At this point, the variables are first_largest equals 5 and second_largest equals 1. Continuing with the array, the next number is 4. This time, it is greater than second_largest, which is 1, but not greater than first_largest. Therefore, we update second_largest to 4 while first_largest remains 5. The variables now are first_largest equals 5 and second_largest equals 4. Finally, we look at the last number, which is another 5. Since it is equal to first_largest, no updates are needed. The final values are first_largest equals 5 and second_largest equals 4. Using the formula, first_largest 1 asterisk, second_largest 1, we calculate 5 1 asterisk 4 to 1, which equals 4 times 3, resulting in an output of 12. In this third example, the array is 10, 2, 5, 2. We start by initializing both first_largest and second_largest to negative infinity. The first number, 10, is greater than first_largest, so we update second_largest to the value of first_largest, which remains negative infinity, and then update first_largest to 10. Now, the variables are first_largest equals 10 and second_largest equals INF. The next number is 2. Since 2 is greater than second_largest, we update second_largest to 2 while first_largest remains 10. The updated state is first_largest equals 10 and second_largest equals 2. Continuing the iteration, the next number is 5. This is larger than second_largest, which is currently 2, but smaller than first_largest. So, we update second_largest to 5 while keeping first_largest as 10. The variables now are first_largest equals 10 and second_largest equals 5. Finally, the last number, 2, is smaller than second_largest, so no updates are made. With first_largest at 10 and second_largest at 5, we calculate the result using the formula, first_largest 1, asterisk, second_largest 1. Substituting these values, we get 10 1 asterisk, 5 to 1, which equals 9 times 4, resulting in a final output of 36. To analyze the time complexity of our algorithm, we can break it down into 3 main steps. First, we initialize two variables, first underscore largest and second underscore largest, to negative infinity. Since this is simply assigning values to variables, it takes constant time, or O1. Next, we iterate through the array nums using a single for loop. If the array has n elements, the loop runs exactly n times. For each iteration, we perform a constant number of operations, like comparisons and updates to the two variables. Since these operations don't depend on the size of the input, each iteration is O1, and the entire loop is O(n). Finally, after completing the loop, we calculate the product of the two largest values minus 1. This is another constant time operation, O1. Summing up these steps, the loop dominates the runtime, so the overall time complexity of the algorithm is O(n). Now that we've covered time complexity, let's look at the space complexity. The algorithm operates directly on the input array nums and doesn't allocate any additional space for the input, apart from the array itself. This means there's no extra memory used for data storage. Additionally, we only use two auxiliary variables, first underscore largest and second underscore largest, to keep track of the two largest numbers in the array. These variables require constant space, or O1. Since no other memory-intensive operations or data structures are involved, the total space complexity of the algorithm is O1, making it highly efficient in terms of memory usage. Let's compare this optimized approach to a brute force method. In the brute force approach, we would iterate through all possible pairs of numbers in the array. For each pair, we calculate their product after subtracting 1 and track the maximum product found. This involves two nested loops. The outer loop runs n times, and for each iteration, the inner loop runs up to n times as well. This results in a time complexity of O(n squared). However, the space complexity in the brute force method remains O1, because no additional data structures are used. In comparison, the optimized approach achieves a significant improvement by reducing the time complexity from O(n squared to O(n), as it finds the two largest numbers in a single pass. Both approaches use constant space, but the optimized method is much faster for larger inputs, making it the clear choice for efficiency. When analyzing the algorithm under different scenarios, the time complexity remains consistent. In the best case, the algorithm still processes the entire array, iterating through all n elements, which results in a time complexity of O(n). Similarly, in the worst-case scenario, the algorithm doesn't change its behavior, it always performs the same number of iterations and operations, so the time complexity remains O(n). On average, the algorithm also exhibits O(n) time complexity, as it does not depend on the order or distribution of the input values. Mathematically, we can prove this by observing that the for loop runs n times, with each iteration taking O(1) time. Adding the constant time operations outside the loop doesn't affect the dominant term, which is O(n). Additionally, since no extra memory is allocated, the space complexity is constant at O(1). This analysis confirms the algorithm's efficiency in both time and space usage. In solving this problem, there are a few common mistakes to watch out for. First, it's important to ensure that you're accounting for the largest two distinct values in the array. Some might mistakenly multiply the two largest numbers directly without subtracting 1 from each beforehand, which will lead to incorrect results. The formula explicitly requires you to compute nums I1 asterisk nums J1, so skipping that subtraction step is a critical error. Another frequent mistake is using nested loops to calculate the product of every possible pair. While this brute force approach works, it results in O(n squared) time complexity, which becomes inefficient for larger arrays. Instead, you should aim for optimized solutions that operate in linear time. Finally, be cautious with arrays that contain duplicate values. If the two largest numbers are the same, you need to handle this scenario correctly to avoid errors in the product calculation, as duplicates can lead to unexpected results if not properly accounted for. Another common issue arises when sorting the entire array to find the two largest values. While sorting might seem like a straightforward solution, it has a time complexity of O(n log n, which is less efficient than the optimal O(n) approach where you directly scan for the two largest numbers. Additionally, pay close attention to indexing. Off-by-one errors or confusion around zero-based indexing are frequent pitfalls, such as mistakenly accessing nums, len, nums, instead of nums, len, nums, 1. These small indexing mistakes can result in runtime errors or incorrect calculations, so it's critical to carefully manage array indices and ensure you're accessing the correct elements. This problem is a great opportunity to demonstrate your ability to reduce computational complexity. By directly finding the two largest numbers in a single pass, you achieve an optimal O(n) solution, which is a significant improvement over less efficient methods. Recognizing this pattern is a valuable skill, as problems involving the largest or smallest values frequently appear in technical interviews. You should consider whether sorting or single-pass scanning is more appropriate for a given context. Additionally, always think about edge cases. For example, what happens if the array has only two elements, or if the largest values are duplicates? Another possible edge case involves numbers close to 0, which can impact the result after subtracting 1. Interviewers may also present follow-up questions, such as asking for the k largest values or introducing constraints like negative numbers. Being adaptable and able to modify your solution accordingly is an important part of standing out in these scenarios. This problem shares similarities with several other LeetCode questions, and studying these related problems can help you build a stronger foundation. For example, LeetCode 215 focuses on finding the kth largest element in an array, which can be solved using sorting, heaps, or partitioning techniques. LeetCode 1046 involves repeatedly identifying the two largest elements, similar to this problem, but applies it in a different context. LeetCode 628 asks for the maximum product of three numbers in an array, which requires a careful analysis of both the largest and smallest values due to the potential for negative numbers. Lastly, LeetCode 414 challenges you to find the third distinct maximum number, which requires tracking unique values efficiently. Practicing these problems will not only reinforce your understanding but also prepare you for variations that may appear in interviews. When considering alternative approaches, each comes with its own trade-offs. A sorting-based approach involves sorting the array and then selecting the two largest elements from the end. This is simple to implement but has a time complexity of O(n) log n, making it less efficient than more direct methods. Alternatively, you could use a heap-based approach, such as a max heap or priority queue, to efficiently extract the two largest elements. This method is useful for generalized k-largest problems and has a time complexity of O(n) log k, but it's slightly more complex to implement. The most efficient solution is the single-pass optimized approach, where you iterate through the array once to find the two largest numbers. This achieves O(n) time complexity, making it the fastest option, but it requires careful tracking of both the largest and second largest values to ensure correctness. Understanding these trade-offs will help you choose the best approach based on the problem constraints and requirements. Great job! To summarize, we solved the problem by identifying the two largest elements in the array and calculating the product efficiently. We also reviewed key takeaways like optimizing array traversal and handling edge cases. Thanks for joining me, and don't forget to like and subscribe for more coding tips. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!